Hi, everyone. Thank you so much for joining us today. I am Camille Couet. I am the Associate Director of the UC Berkeley Retirement Center, and I am thrilled to introduce our speaker today. Dr. Bryan Méndez is an astronomer at the University of California at Berkeley. He teaches classes for the astronomy department, creates educational programming for NASA missions at the Space Sciences Laboratory, and is the planetarium director at the Lawrence Hall of Science. He graduated from the University of Michigan in 1997 with degrees in astronomy, physics, and music, and continued his studies at the University of California at Berkeley, graduating in 2002 with a PhD in astrophysics. Bryan is a family man who loves to spend time with his wife and twin boys, a sci-fi fantasy fan with particular obsessions for Star Wars and Star Trek, a saxophonist, and a film enthusiast. Bryan is multicultural, of Mexican and European heritage, and strives to foster diverse perspectives in his work. So, Bryan, we are very excited to hear about the astronomy of Christmas. Take it away.
Thank you very much, Camille, and welcome everyone. It's such a pleasure to see so many people interested in this topic, and um, I see some names of some old friends. So hopefully you haven't heard all this before. But yeah, 'tis the season to talk about how astronomy is always a part of our various celebrations, and so I'll spend um, our time together here telling you a little bit about Christmas and some of its astronomical origins or um, astronomical influences. And as I go through the talk, please do feel free to drop messages in the chat, and I'll try to keep my eye on those. I always prefer to answer questions kind of in the moment rather than saving them all up for later. I mean, I'll save time at the end too in case things occur to you then, but please do drop them in um, the chat. And if I miss it, Camille, I think, promised to make sure I get to it. Okay, so let's go ahead and start the presentation. All right. And I'm going to move this little window out of the way so that I can see better. All right, so sometimes you might ask, why would astronomy and Christmas have anything to do with each other? And my answer to you might be, well, astronomy actually has a lot to do with everything that humans do for a lot of historical reasons. One of my specialties these days is in cultural astronomy. I teach a class in the summers on cultural astronomy, and a lot of the programming that we do at the Lawrence Hall of Science now is about the connections between astronomy and culture. So there's a lot to be found here. And the way I usually like to start is thinking about time, because there's a real deep and kind of obvious connection, I suppose, between celebrations of holidays and the way we keep time. So let's start thinking about time and how we do measure time. And if you look around the world, just about every culture, and in fact, I can't think of any who don't, and if any of you know of some, please tell me, the basic unit is the day, right? Everyone seems to mark a day. There are then variations on how they mark the day, right? There's different ways to mark the day. You could say mark the day from sunrise to sunset, or from sunrise to the next sunset. You could do it from sunset to sunset, sunset to sunrise, very less common, noon to noon. And then there's, of course, the way we do it, which is midnight to midnight, which is an unobservable, which is fun. Um, and that's what we call our current universal time, is using that midnight point. Uh, all a bunch of different reasons why you might choose those points, and if you do, you'll get slight variations in how long your days are throughout the year, and those variations will also depend on your latitude on Earth. Um, if you were really interested in measuring your time so that each day was kind of the same length, if you tried to do something like sunrise to sunrise or sunset to sunset, you'll find that you're not going to do a very good job of that. You're going to see a lot of variation in your day length because, basically the seasons, and then there's additional things too. But the seasons will change the length of the day on you if you use those measurements. If instead you try to use noon to noon, you'll find kind of the most consistent length of time is occurring. Um, so, the way to measure noon to noon, astronomers, I'll give you the astronomical way of saying it, is that if we imagine the sky is being divided in half between east and west, there's this line that kind of divides it, kind of running from south to north through the middle of the sky. We call that the meridian. And so when the sun passes your meridian, that's noon. Um, and if you're thinking about your daily lives and you look at a clock and you see the clock tells you it's 8 a.m., what that refers to is it's telling you that it's 8 hours ante meridian. That's Latin for before the meridian, right? And then PM, so that's AM. PM stands for post meridian, after the meridian. So when the sun is in the eastern side of the sky, it's AM, and when it's in the western side of the sky, it's PM. The way you might measure this, if you're not an astronomer and don't have fancy tools, you can use the tools of the old astronomers, which is a good old stick in the ground. Put a stick straight in the ground, make sure it's standing straight up and down. You can do that by just hanging a little weight off it and watch the shadow of that stick move. When the shadow is minimum, it's noon. So careful observation will allow you to measure the length of the day pretty accurately just using sticks and shadows. Now, that motion of the sun through the sky is caused by Earth's rotation on its axis. So, Earth is a big old spinning rock, big ball of rock that spins in space, as this animation shows. And as it does so, it creates the appearance of the movement of objects in the sky. Astronomers call this diurnal motion. And the Earth's spin is very, very regular. There are slight variations, but they're caused by movements of matter on the Earth, right? So, if any of you remember some of your basic physics, you know that the moment of inertia of an object depends on how the shape of the object, and how matter is distributed on that object. Earth has things like water and air currents that are moving mass around the planet. There's um, flows of rock that are happening deep inside the Earth. And so all of those slight changes, as well as ice changes, right, where the ice flow is flowing, especially at the poles of the planet, all of those slight changes can slightly change the moment of inertia of the planet and can cause little variations, very small, mostly in the milliseconds of time, but very, um, real variations in the rate of Earth's spin. And then you get those are the internal forces. There's also additional forces from the Earth and the sun, or sorry, from the moon and the sun that can affect the spin rate of Earth as well. But it's, for most of our daily needs, the spinning of the Earth is a pretty good clock. Now, here's a fun little variation that I always like to confuse people with for fun. There's different ways that you can measure this rotation. You can use it by the sun itself. So you can do what we were discussing at the beginning. Put a stick in the ground and measure noon to noon. We call this a solar day, or the fancy astronomer term is a synodic day. It is not equivalent to the rotation rate of the planet Earth. And the reason for that is because the Earth is also orbiting the sun as it rotates on its axis. And so this little figure here is meant to show you, if you start out at point one, you've got your stick in the ground pointing up at the sun at the beginning, and then as the Earth turns, it also is moving along its orbit. And so when the Earth completes one full turn on its axis, the stick is not pointing right at the sun yet. And it actually takes a few minutes more for the Earth to turn and point back at the sun. So this notion of a solar day is actually a slightly longer period compared to the rotation rate of the Earth itself. So if we wanted to measure what that rotation rate is, we would want to use stars because stars are so very far away that our motion around the sun compared to the distance of the stars is infinitesimally small. So we can use the stars as kind of like a fixed reference point, and we could take any star and measure how long it takes for that star to go around the sky, and that would be a measure of Earth's rotation rate. And we call that a sidereal day. So synodic or solar day is relative to the sun, sidereal is relative to the stars, and it's a little bit shorter. So the solar day, a better way to think of it is the solar day is a little bit longer because it takes that extra time to spin around. But because we really are stuck to the sun and we think about the sun, we defined the length of the solar day to be exactly 24 hours. And so this sidereal day by the stars is just about 4 minutes shorter than that. And if you're thinking, so what? What does that mean? Well, this is like one of the reasons why the stars come up 4 minutes earlier every night. So if you're actually watching constellations day after day, you'll notice that day after day at sunset, they're slightly higher in the east every single time at sunset, and that's because they rose 4 minutes earlier every single day due to Earth's motion around the sun. Now, the other unit of time that we see people using across cultures is the period of the sequence of the phases of the moon. And, we know that as a good old month, right? And it's right there in the name, right? Just put an extra O in that and it's moonth. And you can see where the name itself comes from. It comes from this cycle of the phases of the moon. This figure here is meant to show you, real quick why the phases of the moon happen. This moon goes around the Earth, and as it does so, our vantage point from Earth looking at the moon, we see slightly different amounts of the day side of the moon. So at point one, when the moon is between the Earth and the sun, we don't see any of the day side of the moon. So we call that a new moon. And at point three, for example, we can see half of the moon lit up from our perspective on Earth, and we call that confusingly a quarter moon, right? We see half a moon, but it's a quarter moon. It's a quarter moon because it's a quarter way around the around the Earth. So the amount of time to go from new moon to new moon is on average 29 and a half days. Um, There's another name for this, which if you're ever reading about this, it's called a lunation. A lunation is the period from new moon to new moon, or a repeat of the sequence of the phases of the moon. So if we look at actually some of the oldest calendars that we have archaeological evidence for on Earth, we actually see that most of them are using the moon cycle of phases as kind of there's the day, and then there's a count of 29 or 30 days that make up a month. And we see cultures around the world counting time that way. Now, it's reasonable if you were thinking, okay, there was a synodic and a sidereal day. Is there also a synodic and sidereal month? And the answer is yes. There is. The synodic or the solar month is actually the one we just talked about, the phases of the moon, because new moon to new moon is an arrangement with the sun, right? It's when the moon is between Earth and the sun. But just like when we were talking about the sidereal and synodic periods on Earth, we've got the same thing happening with the moon. The Earth is moving in its orbit around the sun as the moon orbits the Earth, which means for the moon to take one complete trip around the sun, if we start here at point one at a new moon, when the moon gets back to that same arrangement between the Earth and the moon, it's not a new moon yet. It's actually a waning crescent. The moon has to move a little bit more in its orbit around Earth in order to come back to a new moon configuration. So the period of the lunation is actually longer than the sidereal period. So relative to the distant stars, it only takes the moon 27.3 days to come back to the same arrangement with some group of stars, whereas it takes that 29.5 days to come back to a new moon arrangement with the Earth. So that's again, that's something that, you probably don't notice so much unless you're watching the moon relative to stars and then noticing that, hey, the last time the moon was next to that group of stars, it was in a slightly different phase. And that's because of this, these two motions adding together. Now, I'll mention a couple of early calendars. Well, actually, this one's not as early, but it's a fairly simple calendar that just uses these two things that we talked about, days and months, and lunar months. And the Islamic Hijri calendar is a very simple calendar. It just counts days, and it counts them in groups of 20 or 30. And that makes up a Hijri year, is a group of 12 of those. So 12 months makes a Hijri year. And there is no connection to the seasons of the sun. It's just a purely lunar calendar. And the oldest traditions of this calendar are really cool. They used to employ astronomers whose job it was to go and spot the crescent moon right after the new moon, because that would mark the beginning of the next month. And the official start of the next month wasn't declared until the astronomer saw that crescent moon. And so, if it was cloudy that day or they overslept or whatever, the new month didn't begin until the official astronomers of the state saw it. And so sometimes you could have different cities throughout the Islamic world in slightly different months if their astronomers in that city had observed slightly different timings. Nowadays, they kind of use official tables to keep the Hijri calendar. And because it's a kind of rotating back and forth between 29 and 30 days, because the new moon to new moon cycle is not an exact number of days, right? You'll see that the length of a Hijri year can range either to about 354 or 355 days. As I said, again, this is not tied to the seasons, which means that the seasons will move throughout the calendar. And so the holy month of Ramadan, for example, which is the month where Muslims will fast during daylight hours, it moves around the seasons. And sometimes Ramadan is in the summer when days are very long, which means fasting is harder because it's a longer period of time. Sometimes Ramadan is in the winter when the days are short and it's a little easier. And apparently, there are some concessions made so that if you wish to move your Ramadan observances um, from one season to another, some traditions allow you to do that to maybe average it out so that those extremely long summer days are not made even longer by not being able to eat or drink during that time. Moving on to talk about the seasons then. The seasons, as we experience them on Earth, we experience them in a number of different ways. For example, if we watch the sun where it rises on the horizon, we can see that it goes through this kind of cycle of rising very far north of east to rising directly in the east and then to rising south of east. And so when it's rising very north of east, that's our summertime. When it's rising very south of east, that's our winter time, at least in the northern hemisphere. I'll be very northern hemispheric central for us today. Know that whenever we mention things about seasons, it's always opposite for the southern hemisphere in terms of the timing. So, those are some of the things we notice. The height that the sun reaches during noon changes with the seasons. It's highest in our sky in summer, it's lowest in our sky in winter. We're coming up on that lowest point in the sky. Just this coming Saturday will be that period of the longest night, shortest day, lowest location of the sun in the sky. And the reason that we have this variation in seasons is because Earth's axis of rotation is tilted relative to the plane in which it orbits around the Earth, or sorry, around the sun. If they weren't tilted at all, if it was like perpendicular, then the sun would rise and set from the same location on the horizon all year long. There'd be no variation and we'd have no seasons. So here's a picture to try to depict a bunch of different things all in once. It's showing you the Earth's orbit around the sun. It's showing the axial tilt and showing you how that changes the amount of daylight different parts of the planet receive at different times of the year. And we pick some of the special places along this path as special times. They're called quarter days, and they mark um, when we have longest days, shortest nights, wait, longest nights, shortest days, and the special days when you have equal day and night, called the equinoxes. So that's shown here in this picture. So this is a kind of a top-down view to give you that sense. So you can start with the equinoxes, which happen in March and September. That's when the tilt is kind of not tilted toward or away from the sun, and it kind of doesn't matter, and we get equal days and nights. And then you can see how the tilt in June of the North Pole toward the sun leads towards longer days in the north. And likewise in winter, which we're coming up on here in December 21st this year, um, the North Pole is kind of pointed away from the sun, and therefore we get much shorter days in the north. The amount of time it takes to go from one of these special alignments, one of these quarter points, and let's pick the solstice, right? To go from, say, winter solstice to the next winter solstice, or to go from one June solstice to the next June solstice, that is what's called a solar year, or sometimes it's also called a tropical year. And the value of that is 365 days, 5 hours, 48 minutes, and 45 seconds. In decimal, I always just shorten that to 4 decimal places and think of it as 365.2422 days. That's ingrained in my memory anyway. That's the length of the solar year. So it's relative to the sun because it's the arrangement of the axis of the Earth with the sun, and we get a repetition of the seasons with this cycle. As you might guess, if there's a solar year, is there a sidereal year? You betcha, there sure is. And in this case, the way to do it again is with the stars. And since we're doing the sun, we would kind of say, okay, let's look at a group of stars and see when the sun is aligned with them. How long does it take for the sun to align with them again? That would be the measurement of how long it takes for Earth to make one complete circuit around the sun, so to complete Earth's orbit. Now, it sounds like the same definition of the solar year, but it's not quite the same. And the reason for that is because Earth's axis is wobbling around in space. So if you imagine spinning a top and you can watch it wobble around, it does this little wobble. In physics, we call that wobble a precession. Earth's orbit precess or Earth's axis precesses around in a circle, and that creates the amount of time from one solstice to the next to actually be different from the amount of time that it takes Earth to just make one complete circuit around the sun. What it does is it ends up creating a slight difference between those two cycles, which adds up to about 1 day every 72 years. So that means if we had a calendar that was marking the alignment of the sun with a spot in a star, we'd see that alignment shift every 72 years by 1 day in our calendar. So this is called the precession of the equinoxes. It's why, for those of you who are fans of astrology, it's why the sun signs are a whole month off from where they were 2,000 years ago. So when Ptolemy came up, the Ptolemy of the famous Greek astronomer who lived in Egypt most of his life, he came up with kind of the modern version of astrology that many of us see in the daily newspapers or whatever. And he had this alignment of when the sun was in certain constellations. Well, and the dates in which that happened. The sun always ends up in those constellations at some time, but the date keeps changing because of precession. It's been 2,000 years since then, and that 2,000 years adds up to a whole month's worth of shift. So all of the solar alignments are a month different than they were 2,000 years ago because of this. All right. Now, there are some calendars who try to combine both the lunar cycle, which is kind of that first cycle that humans really paid attention to, and that solar cycle, which we started to really care about when we became farmers, right? So when humans invented agriculture, and it became extremely important for our survival to be able to know exactly when we should plant our crops, when we should reap the crops, then it became really important for us to be focused on those seasonal cycles. So then people tried to put together the two calendars, and they found out that because those two cycles aren't related to each other, it's pretty hard to find an exact match. They're not going to fit together exactly, and so you end up with, kind of these mismatches in the two rates. Kind of the best you can do was well, I should say one of the earliest known calculations of a cycle in which you can get them to match really well was done by a Greek astronomer who was called Meton. He was from Athens, and so it's called the Metonic cycle. And it's a period of 6,940 days. So that's 19 tropical years, and that's 235 cycles of the phases of the moon. And that's a pretty good match. And so, if you have a calendar that's marking both lunar periods and the seasonal periods, there's going to be a shift between those things that only repeats every 19 tropical years. All right, so another way to think of that is you've got a date, let's say the summer solstice, and the phase of the moon that occurs on that date. Let's say it's a first quarter moon. The next time that that same first quarter moon will occur on that solstice would be 19 years later. And because these are still not exactly the same rates, there's going to be some slip over long periods of time. And so about every 190 years, you're going to get a 1 day slip in that alignment. So if you were making a calendar that was trying to use the Metonic cycle, that means every 190 years, you're going to have to either skip a day or throw in a leap day to bring everything back into alignment. The Chinese calendar is an example of a calendar that does try to combine the two cycles, the solar and the lunar cycles. Um, it does so in kind of a looser way that's not entirely rigid. There's a couple other calendars that also do this. The Hebrew calendar is another example. Chinese calendar is one of my favorites because it's really complicated. I won't go into all the details, but it was clear to me that when I started researching this calendar, that the ancient Chinese astronomers were making sure that they had job security, right? They wanted to make sure that nobody else could calculate when the next leap month was going to be. So I won't go into the details of that, but I will tell you that the basic features of it are like the Hijri calendar. It has lunar months that begin with the new moon, and they vacillate between 29 and 30 days. There are 12 of them in a regular year, but because of the Metonic cycle, they're not exactly matched. And every 3 or so years, you're going to need a 13th lunar month in your year in order to keep them matched with the seasons. The solar rule that the Chinese calendar uses is that the winter solstice needs to occur in month 11. And that's kind of the basic way that it stays connected to the seasons. Like I said, there's going to be a need for a 13th month every 3 years or so. And the complexity of deciding which month is going to be the leap month is where the Chinese astronomers really showed their mettle. I won't go into that one since we want to talk about Christmas. So we'll get moving on. I do want to mention a calendar that decided to ignore the lunar months and also ignore the fact that the solar year is not an exact number of days, and that is the Maya calendar. Or well, there's many Maya calendars. There's a Maya calendar which is called Hab in Yucatec Mayan language, and it is a 365-day calendar. It is solar because that's kind of its main purpose. Um, and it just repeats every 365 days. It has kind of what we might consider months. It has subdivisions, which are about 18. There's 18 months of 20 days. That gives you 360 days. And then they have a special month that's only 5 days long that happens at the end of every year. And so that gives them their solar year. Now, the Maya mindset was a lot around regular rhythms. They really didn't like the idea of syncopations. And so the notion of putting in a leap year and putting an extra day that would make one year slightly different than the next, they didn't like that idea at all. To them, it was just better to know that solar alignments were going to change over time, right? That the date of the solstice was going to occur on a different day next year. And so for them, that was just a better thing to do. They just preferred doing that than trying to keep the solstice on the same date in the calendar every year. And we know that they tracked it. We've seen some stone inscriptions that show. I put it in the slide here because I wanted you to see the numbers. They calculated that 1508 Hobbs was equal to 1507 tropical years. When you divide that out, that actually comes out to 365.2422 days. So that means they knew to within 1 second, and probably better, because the Maya really didn't like fractions. They liked really big ratios of two, two large numbers. They were always looking for how the wheels fit together, if you will. So their knowledge of the tropical year was very, very precise, and clearly it just wasn't important to them that they matched their dates to that calendar. All right. Before I get into the Christian calendar, I want to mention the 7-day week because it's a feature that you've seen in a couple of the calendars that I showed, which is not necessarily an original feature to those calendars. It's kind of both the Hijri calendar I showed you and the Chinese calendar both had their days aligned in these 7-day weeks. That's more because of the influence of European calendars. But the 7-day week is kind of an interesting because it's kind of its own little calendar that kind of appears in history a few thousand years ago, and interestingly has been used in an unbroken way. The cycle of Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday has been unbroken as far as we can tell for at least 2,000 years, which is pretty amazing to consider. We have records of it going back to the first Easter celebrations in the 4th century AD. Where the 7 days comes from, there's a lot of different suppositions. There's traditions, of course, in the ancient Babylonian and Hebrew traditions of the 7 days being related to the 7 days of creation that are in the story of Genesis, right? So God creates the earth in 6 days, and then the 7th day he rests. And in the Jewish tradition, for example, the Saturday is that day of resting, the Sabbath. And in later American Christian traditions, it got shifted over, right, to Sunday being the Sabbath day. There's some other possibilities for where this comes from, some of which are astronomical. One is that, the moon's cycle of phases, if you divide it into 4, is almost divisible, almost comes out 7, not quite, but almost there. And so, the lunar cycle is kind of nicely divided into groups of 7 days. The other thing that's of interest was that the ancient Greeks and then the Romans recognized what they called 7 planets in the sky. And these were not the planets as we think of them now, but these were the 7 objects that move with respect to the stars. And so those are the 5 planets that we know about: Mercury, Venus, Mars, Jupiter, and Saturn. but also the sun and the moon, because the sun and the moon also move relative to the backdrop of the stars. And so those are the seven planets, the seven wanderers of the sky. And when we look at the naming convention in ancient Rome, for example, we can see that connection, right? The Sunday, as we know it in English, actually is one of those ones where it connects directly from English through. You can see the throughput, but it was in Latin in the Roman Empire, it was called Dia Solis, so it's the day of the sun. And you can see here that the next day was the day of the moon, the day of Mars, the day of Mercury, the day of Jupiter, Venus, and Saturn. And that tradition then carried through to Germanic speaking countries as the Roman Empire was spreading throughout Europe. And they would take some of the characters in the pantheon of gods of Germanic speaking people to try and make those connections. And so Sunday was connected with, or I should say, Dia Solis was connected with the goddess of the sun, whose name was Suna. And that's where, of course, we get Sunday. The moon is from the god Mauni, and that's where we get Monday. Tu was a character in Norse mythology who was kind of a warrior god, and that's so he was associated with Mars. Um, Mercury and Odin aren't quite the same characters, but I think they were maybe the leftovers in the in the overall um, system. And so you can see how this system works. And I'm noticing there's a couple of comments in the, I'll take a pause in the chat just to mention them. Let's see. God in Genesis was non-exempt. Okay, very nice. Joke. And then there was a question about Napoleon trying 10 days, and then someone said not Napoleon, but some. Yeah. So for sure, there's been other attempts at different day lengths of the weeks, and the 7 day week is just an interesting one because of these kind of connections that we have with some astronomy, as well as these other cultural stories. So let's get to the Julian calendar, which will lead us to the story finally of Christmas. So in Rome, they had a lunar calendar um, prior to the rule of Julius Caesar. And as I mentioned, once agriculture becomes important, the sun cycle becomes more important. And so during the rule of Julius Caesar, it was decided to switch over to a calendar system that instead of having lunar months, it was just going to be completely tied to the sun. And so the Julian calendar, named after Julius Caesar, he didn't come up with it, I presume. Maybe they asked him some of his ideas, but it was enacted during his rule in 45, which we now consider 45 BC. Back in the time of Rome, they would have not considered it because they didn't know that Christ was coming, right? So the reckoning that they used was often called AUC, which referred to kind of the theoretical or the mythological founding of Rome itself. And so that the year that this was enacted was 709. So 709 years since the founding of Rome. And the idea was to have months, and they would kept most of their names from the original months. But they did add or change some names, for example, July and August, named after uh, the first two Roman rulers. And um, the idea was that this solar calendar would have would try to be very closely aligned to the seasons by having leap days. So what they did was every fourth year they would have the year contain 366 days. And therefore every 4 years the average is 365 and a quarter. Because the slip is about 1 day every 4 years, right? That's 365.2422 is almost 0.25. So by having this one leap day every 4 years, you get a pretty good match to the solar cycle. And dividing up the new months with days, you ended up with 30 and 31. And because they were going rather than 29 and 30, they ended up with one month that kind of got shortchanged. And of course, that's February. So that's why February ends up being the leap month, the month that gets the leap day during leap year, because it was already shortchanged, and so you might as well give it at least one day back during the leap year. So this is a pretty good system. It worked for their purposes, pretty simple, and it only slips relative to the solar year about one day every 120 years, because it is a bit of an overcorrection, right? The Julian year is a little bit longer than the true tropical year. So that means it's going to get kind of ahead of the overall um, cycle of the seasons. Now, over time, this calendar was very successful and used throughout the Roman Empire. And over time, there became this notion of, instead of using the reckoning of the founding of Rome, to use a reckoning that went back to the birth of Christ. And um, it took a while for this idea to be come up with, and then even to catch on. It was invented by a Roman monk whose name was Dionysius Exequius, and he, through a variety of different kind of calculations of historical documentations from the Christian Bible, as well as some astrological um, numerology, he thought he could calculate what the year was that Christ was born, and count then all of the years in the Julian calendar since then. And so he calculated that he was living in the year 525 AD when he established this year of our Lord in English, or Anno Domini in Latin. And then, of course, so sometimes we now use CE for Christian era, or the Common Era is another way of um, stating that. And so all dates that happen before the birth of Christ are now thought of kind of going backwards. So they increase in time backwards, and that's called BC. Um, Even though this was kind of invented in the year 525, it really didn't catch on in Europe for quite some time. It wasn't until the year 731 that a Saint Bede was writing a book about the history of the English people, and he started using that this dating system in his history, and it kind of caught on, at least across a lot of Europe at that point. One thing of note is that many modern theologians and scholars have determined that Dionysius's math was off a bit, and that a better guess for the um, when Christ would have been born, based on the actual reign of King Herod in Judea, for example, would have been probably somewhere between the years of what is now 6 or 4 BC. Now, the date of Christmas itself is December 25th, which I'm sure you're all familiar with since it's coming right up on us. And this date corresponds to, and I saw some people in the chat mentioning it, to ancient Roman festivals that are essentially a celebration of the winter solstice. The first time we actually see Christmas being celebrated on December 25th is around the 4th century AD. That's around the time of it's I think 425 was the year of the one of the councils of Nicaea, where the Catholic Church was starting to really establish some of their dogma, which we still live with today in Catholic traditions. And so that date of the 25th occurs around that time, and it was using the Julian calendar. Now, that date doesn't come from nowhere. Again, it's pretty close to even in the 4th century, it was very close to the date of the winter solstice, but not exactly. The Roman festival called Saturnalia was celebrated during that period. Saturnalia comes from the name of the Roman god Saturn, who is the god of time. He's the god of agriculture and abundance. He's actually, I mean, he's kind of equivalent to the god Kronos in Greek mythology, but seen very differently. Like Kronos is a villain who ate his children, right? Whereas Saturn is a hero who brings abundance and freedom to the people of Rome. One of the uh, uh, one of the things that was done during the festival of Saturnalia was that the slaves were allowed during this week period to dress in the same dress as free people, and they would even have their masters wash their feet. And it was like this period where everyone was equal with each other, and everyone celebrated the great bounty that they had from that year's harvest. So it was a happy, joyful time. It was seen as a time of renewal because you're kind of passing through the longest night, and now the days will start to grow longer and longer again. So it was seen as this period of renewal. So it was kind of the turning over of the year, which again, Saturn being associated with time, that was also a part of this. The dates of this festival around the time that the Julian calendar was enacted in 45 BC, the dates in the calendar were December 27th through the 23rd, but the 25th was still recognized as, or kind of noted as, the date of the solstice, even though the actual solstice was occurring on the 23rd in 45 BC. But the festival is really old, right? The Romans had been celebrating this festival for centuries. And if you go back a few more centuries before the enactment of the Julian calendar, um, December 25th would have been the date that the actual solstice was occurring on. And this is often the case, is that sometimes people, in an ancient point in history, they notice this solar alignment with a date, and then they just declare that that date is the solstice, right? So December 25th was just always thought of as the solstice, even if it wasn't, in fact, the longest night of the year. And that so that tradition of the 25th being the solstice kind of stuck around even into the 4th century AD, when the idea of celebrating Christmas at this time was starting to come around. So Christmas is essentially a winter solstice celebration, right? Even though we've got these slips of time due to due to the slight offset of the calendar with the solar period. Now, I should mention that over time, uh, this slip started to become a problem for the Catholic Church. This one day every 128 years, it wasn't a problem unless, many, many centuries go by. And by the time of the 16th century AD, the actual spring equinox was starting to happen on March 11th as opposed to the 21st. And that was causing a big clash in the liturgical calendar of the Catholic Church. The Catholic Church has these seasons in which they celebrate different things, and the Christmas season begins December 25th and then continues for 40 days afterward. And then the season of Lent will begin shortly thereafter. Lent is based on when Easter happens. Easter depends on the spring equinox, the phases of the moon, and the 7-day cycle of the week. So all three of those cycles have to come together to set the date of Easter. And every once in a while, when Easter is early, I should say this, Lent begins 40 days before Easter, always. But occasionally, when Easter begins early because of the cycle of the moon's phases, you would have the case where Christmas wasn't over yet, right? The 40 days after Christmas hadn't ended before the 40 days of Lent were supposed to start. And so the Catholic Church were pulling out their hair. Oh my God, what are we going to do about this? We have to fix it. And so in the 16th century, during the reign of Pope Gregory the 13th, they decided, all right, first of all, we're going to reset the calendar so that it's fixed. And then we're going to come up with a new rule that will keep it fixed for a long, long time. So what they did was that in October of 1582, they skipped 10 days. So Thursday, the 4th of October, the next day was Friday, the 15th of October. And so they just skipped those 10 days. So they reset the calendar, right? So now it's back. We aren't going to have this problem. And then they come up with a rule that will fix it for, as long as it can possibly be fixed. And the way they did that was by removing one uh, or sorry, by removing 3 of the leap years that happen every 400 years. So if you think about it, the Julian calendar, every 4 years you got a leap year. And what the Gregorian calendar did is that when you hit the year that ends in 100, they said, all right, we're going to remove that leap year. That one's not going to happen unless it's a year that ends in divisible by 400, right? So, for example, the year 1900 was not a leap year, but the year 2000 was. And this little trick of removing those 3 leap years every 400 years manages to avoid the slip that we had been seeing for those centuries. And it actually keeps it synchronized pretty well for at least 3,000 years. So basically, you go over 3,000 years before you get even a 1-day slip in this new system. So that was a pretty clever thing they did, I think, right? They reset it so that it's back to the way it should be. And then they come up with just a slight tweak that keeps the calendar synchronized with the actual seasons. One of the things, it doesn't affect Christmas's date. They just set Christmas to be the 25th always. The winter solstice now kind of stays fixed on the 21st or the 22nd because the calendar is now so nicely synchronized with the seasonal cycle. So there's my explanation of that slip. We can skip that slide. We know our calendar pretty well. I wanted to mention that you can talk about the same kind of story of the dates of holidays and look at their astronomical connections. And especially with the Catholic Church, there's a lot of versions of how it's kind of attached to these older festivals. One of my favorite examples is the festival of Samhain, which was a Celtic harvest festival that happens in what's called the cross quarter days, the in between the equinox and solstice days. And this was a festival that marks the end of the harvest, the beginning of winter. And when Christianity was kind of taking hold across Europe, the idea was as we try to convert the local population to Christianity, let's not just make up a whole bunch of new festivals for them. Let's give the old festivals a makeover, right? So the festival of Samhain became All Souls Day, right? And so you celebrate All Souls Day on the same day. And so All Souls Day, even though it doesn't have anything to do with seasons, ends up becoming tied to the cycle of the seasons. Likewise, Groundhog Day is another fun example of that. One thing I want to mention before I end is just, which I think is a kind of a fun irony of astronomy, is that, a lot of all of these measurements of time that we've just talked about begin with astronomical cycles, but in the most recent century, astronomers have realized that because the motions of the Earth are not, are a little bit variable, we actually need now to have units, definitions of time that are more accurate than the motions of the Earth itself. And we redefined the second in order to make it more precise than, a subdivision of the Earth's rotation, which is how it was originally defined. So I just wanted to throw that out. And then we also decided, there's so many ways to measure a year. For astronomers, we're just going to say that a year is equivalent to a Julian year, 365 and a quarter days done and done. We're just going to call that a year for our purposes. Why? Because it's a nice even number. And the last thing I think I'll mention here, because I know we're getting to the top of the hours. I know a lot of people, when you say the astronomy of Christmas, they go to the Star of Bethlehem, and they're, oh, what was the Star of Bethlehem? And I don't have to say too much about this, but I'll say a little bit about it, which is that, the Star of Bethlehem is only mentioned in one of the 4 Gospels. And there's not a lot there. There's not a lot that's said. It said that there were these magi who came from the east. They said they saw a star, and it told them that, or their interpretation of it was that the king of the Jews had just been born, and where is he? And King Herod, when he found this out, was like freaked out, like, what? I'm the king of the Jews. Nobody else is the king of the Jews. You go find this king of the Jews somewhere and tell me about it, right? Go follow that star and tell me about it. And then they go off and they followed the star, and the star led them right to Jesus. And then an angel came to them and said, by the way, don't tell Herod what you found. And they're like, oh, okay. And they just went home. They didn't tell Herod. Good for them. That's what the story said. What the star was, who knows, right? Over the years, there's been lots of speculation that it, could be some kind of natural astronomical phenomenon. There's all kinds of transients that happen in the sky. There are things like comets. There are things like nova. There's the Magi were most likely astrologers, meaning they were kind of their bread and butter was reading signs in the stars. And so maybe something like a conjunction of Saturn and Jupiter would have been significant to them and kind of made them think that this was some kind of fulfillment of the prophecy that was in the Old Testament about the birth of the Messiah. Um, but of course, the gospel doesn't say any of that. That's all supposition. Who knows, really? There was a Saturn Jupiter conjunction in 7 BC that happens about every 20 years. So, was that something, why that time that Saturn and Jupiter were in conjunction with the Magi think, oh, the Messiah has finally come, and not 20 years before, 20 years after, right? One of the things that I note is that the way it's described in the gospel is very unnatural, right? It's not normal for a star to hold its position in the sky and lead someone along a bearing. Like that, there's only one star that does that. That's the North Star, and that's because the North Star is located directly above the axis of Earth's rotation, right? And so all other stars, they move, and so following them doesn't take you anywhere. It just kind of makes you go in a zigzag. Um, One thing I always like to think about when I'm thinking of things like this is, okay, well, how could it have happened? Right? What would you need to create a star that would actually take you from Jerusalem to Bethlehem? And so I realized that, well, you could do it with a satellite that's in geostationary orbit that would appear to stay in one fixed location in the sky, and you could follow that along a heading. It would need to be really big because geostationary orbit's pretty far away from Earth, tens of thousands of miles. So in order to be visible to the human eye from that location, it would be a very giant object. So, there's another little supposition to throw into the question of what was the Star of Bethlehem. Okay, that's the main astronomy of Christmas that I intended to tell you about today.